So from this point on, we're actually recording this session. And the first thing that I want to do is I want to review the very important material that we started with last week, the stuff that we're really going to build on this week and the beginning of next week to really kind of get a handle on where we're going with this, where we're going this semester, and how we're going to be using statistics in the future. So one of the things that we noticed is, let me move this over a bit. One of the things that we learned is that when we have a measurement that involves a population, let's say a numerical measurement like blood pressure or something like that, right? When we have something like that, we know, and we have a population. Population is a whole group of people, whatever we define as a single monolith or group of people. Very frequently, we want to understand what the average blood pressure, what the mean blood pressure is for that population. We want to understand where the middle is, because the middle tells us a lot about what a normal blood pressure might be, or what how one blood pressure of one group might compare to another blood pressure. So very often we're looking for the middle, the mean, or the median. Or sometimes if it's categorical, we look for the proportion, which is kind of like another version of the mean or the median, the middle, right? So the only problem is that we never know what the true mean is, because we never sample and know about an entire population. So let's say that there are 30 million diabetics in the United States, say 1 out of 10 people or something like that, or pre-diabetics for that matter. And we were curious about what the average blood pressure was of pre-diabetics in the United States. We're not going to have the money or the resources to go around and measure the blood pressure of 30 million people. However, what we can do is we can take a sample of people around the United States and find the average blood pressure for that sample of people that we measured, whether it's 100 people or 200 people or 1,000 people or 5,000 people. We can find the average for that sample. And based on what we've learned so far, we know that when you take a sample, what you're using that sample for, the reason why you're using that sample is because you expect that the average of the sample is going to approximate the average or the mean of the whole population. And the bigger the sample is, reason would suggest, the more likely that the sample is going to be a good reflection of what the population is going to be. Obviously, if my sample size is 1, well, then it's a real crapshoot. I don't know if I'm going to get anybody who's anywhere near the average population. If it's 2, I got a little bit better chance. If it's 10, a better chance. If it's 30, I got a much better chance. If it's 1,000, it's an even much better chance. So really, what we're really interested in knowing is what the mean of the population is. And we refer to the mean as the population as mu, right? That's our mean for a population. Since we're never going to know that, that's always going to be unknown, right? Actually, let me back that up for a second. There is a situation where we know, for instance, every bit of, we measure every person in a population, and we know, for instance, what the number of children they have is, so on and so forth, some other parameters, what their income range is, and so on and so forth. How do we know that? What is that? Where is it that in the United States that we actually measure everybody? We don't do a sample, we actually measure anybody. Take a wild guess. What do you think? When does that happen? I'll give you a hint. It happens every 10 years. The census, right? The only time we really measure the entire population in general is when we do a census, when we measure everybody at the same time. In fact, in the Constitution, it requires that the census be a actual count. It can't be statistical. So in other words, we can't say, yeah, we could measure 1 out of 10 people, and we could randomly select 1 out of 10 families, and statistically we would have a really good idea what the population is, and so on and so forth. And we would save a ton of money doing that, right? Because they actually send census. If you don't reply to the census, they send census takers out to knock on your door, and so on and so forth. Save a ton of money doing that. Unfortunately, And not only that, but there are a lot of people that tend to shy away from the census, that are unlikely to respond. Elderly, people that have physical disabilities, people that are undocumented, for instance, they'll avoid census takers. But we know, because they send people out to try and track people down, we know that we could actually improve the quality of the census by following up and tracking down how many people are being missed because of this undercount and correcting for it. But legally, they can't do that. The representation, distribution of tax money, so on and so forth, is based on an actual count. According to the Constitution, it can't be corrected using other methods like statistical methods. So it's kind of weird, right? That doesn't happen so much. But that highlights the fact that in general, we don't know what mu is. We never find out what mu is. So our best guess at what mu is to take a sample and find the mean of the sample. Now, mean of the sample, we won't use mu, we use X bar. We'll use our own alphabet, X bar, instead of a Greek letter. The other thing that we're interested in knowing about in a population is, we know if we take a sample from a population, if we randomly sample from a population, the first person that I take, if the mean is, let's say I'm talking about blood pressure, the mean is 80, right? If mu is equal to 80, the first person I select, I have just as good a chance that selecting someone that's less than 80 as I have selecting someone that's above 80, right? It's just purely chance, right? What I might get. So when I take a sample from this population, I'm going to be getting blood pressure readings from many people, let's say 100 people. So first person might be 73, second person might be 80, 83, next one might be 80, 80, 81, 84, 75, 90, right? So I am going to get numbers that aren't necessarily, or you would expect, are not going to be exactly the same as the true mean of the population. Well, we've learned, because since we're taking a random sample, whether we're getting people that are above the mean or below the mean, the way that's determined is just by chance, because it's random. And one of the things we're starting to understand is that random events, probability, right? Chance is predictable, right? Kind of is a contradiction in terms. Chance is predictable, right? And the way that it's predictable is that we understand that when we take samples like this, they're going to follow certain patterns. And one of the patterns is that the distribution is going to have, if it's truly due to chance, it's truly a random sample, the distribution is going to have certain characteristics, and they might look like that's the best one I've drawn in weeks, right? That they would be distributed normally. Well, what does that mean, normally distributed? Well, that means that as I sample people, just like that representation of the binomial distribution, as I sample people, I might sample people and put them into a bin that represents 70 to 72, another bin that represents 74, 72, 72.1 to 74, and so on and so forth. And one bin over here is 80, 80, 79 to 80, and so on and so forth. And as these bins get closer and closer to the mean for that population, I will have more and more people that are close to that. In other words, if the average blood pressure for our population is 80, then the most likely outcome, if you randomly sample someone, is that you're going to get somebody that's close to 80. And it's going to get less and less likely as you get further and further away from 80. So it's going to be more likely that you'll find people whose blood pressure is 79 than, say, 75. And once you get down to 70, it gets very unlikely. As you get further and further away from the mean, it gets less and less likely. So if I draw that as a histogram, you see it as bars. If I take an infinite number of people or an entire population, there'll be so many people that will actually kind of ease out into a bell-shaped curve. There's actually a formula for this bell-shaped curve, and the formula is the 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 representation of the effects of chance on our normal distribution, right? It's gonna be a representation mathematically. So let me see if I can't find that quickly. Normal distribution formula. Okay, let's see if I can't find it. Okay, here we go. This formula right here. This formula represents the height of that line. F of x would be kind of like saying y-axis. So this formula tells us the height of that line of that bell curve is equal to, and let's not worry so much about the complexity of this formula. Just let's look at what that height of that line is determined by. It's determined by the standard deviation, the spread of the population, measure of the spread of the population, and it's determined by the mean of the population, and it's determined by the value at that point, wherever it is you want to know the height, whether if mu minus if you're talking about right at mu, it'd be mu. This would be 0, so it would just be equal to this. But and we would see that this y is determined by this formula. So if I go back, and let me just reprieve the binomial formula. Okay, that distribution is represented by this formula, which we were looking at before, right? So even though these are events that are due to chance, they become predictable when we understand them mathematically. You're not going to be required to work with or use these formulas or anything like that. Just understand that based on these calculations, these formulas, the mathematical nature of probability and chance, we can do a lot. We can predict a lot about how things are going to be distributed. So this normal distribution that I'm looking at here, this distribution of expected values for a population described by where its mean is and how it's spread out is going to look something like this. I'm going to open up a new page, a clean page. Okay, so what's this going to look like? I'm going to take my normal distribution, and the middle of this value is going to be 80 for the one I just described. So that's 80. And this is going to describe, for now, this is going to be a population. Okay, and the spread is going to be represented by sigma, the standard deviation for this population. I'm going to say for argument's sake, it's going to be equal to 10 in our case. Okay, so what does that tell us about this population? That tells us that if this is a truly normally distributed population, then I can make a lot of predictions about this, right? So I can say, for instance, that 68% of the people in this population are going to have a blood pressure between 70 and 90. Right? Anybody remember what that rule is? Remember what that was called? How about you guys? Remember what that rule was called? That's called the empirical rule. Great, great, Edge. Thank you. It's the empirical rule, right? That's exactly what we were talking about before. Now, this is an estimate. I think the book even calls it 68, a little bit more precise, calls it 68.1%. And that represents the middle, that gives us a prediction about the spread of this population in terms of blood pressure. You can look at this a couple of ways. One way you can look at it is to say 68% of the population has a blood pressure between 70 and 90. The other way you can look at it is a probability, where the whole area of this distribution represents 100%, or 1 if you look at it as a fraction. And the probability that an individual that you picked at random would be between 70 and 90 with the blood pressure is 68%. You could look at this area as representing the probability that you would select someone from this population that's in that range. Okay, and the other thing that we knew is that there's actually more to this empirical formula, that we could also say that if I want to know 95% of the population, right, that would be represented by 2 times the standard deviation, 2 standard deviations, or between 60 and 100. So basically, we're saying 80%, 95% of the population, I'm sorry, 95% of the population is within 2 standard deviations of the mean. In other words, between 60 and 100. Okay. And we also had a rule for 90 for 3 standard deviations and so on, but I'll stick with these two for now. So that's going to guide us quite a bit in terms of what we're going to be able to do in terms of understanding this population. And it doesn't matter what the shape of the distribution was. So, for instance, let's say instead I took a smaller population, maybe population of 12-year-olds in New York City public schools, and measured their blood pressure. And it turns out that their average blood pressure was also 80, but their distribution was much narrower. In other words, the standard deviation was equal to 2 instead of 10. Well, what does that tell you? The same rule applies. That tells us is 95% of these students, their blood pressures are going to be within 2 standard deviations, below the mean and above the mean. But since the standard deviation now is 2, 95% of them are going to have a blood pressure between 76 and 84. This rule, this empirical rule, always holds up for normal distributions, even if the standard deviations and the means are different. Okay, guys, we have that. Does that make sense? Right? So that's going to be a valuable tool for us moving forward. Okay, so let's move on from there and try and apply this a couple of ways. Okay, so I'm gonna kind of reprise a couple of versions of a couple of problems that we solved last time we got together, and I'm going to give you a population, and I'm going to say that the population is, let's see, what kind of measurement can I work with? I'm going to look at blood lead levels for children in New York City, in Flint, Michigan. Right? We had a problem with that recently, right? I'm going to take a look at their blood lead levels, and we're going to sample every child in public school in Flint, Michigan. They probably have done this already. You know, that's part of the reason they know that they had an issue is because they were screening children as they entered elementary school in Flint, Michigan, as they do here in New York. Let's say we measure all of them, and we find that the average blood lead level for this is usually measured in micrograms per deciliter, right? That's billionths of a gram per tenth of a liter of blood. Okay, so let's say that mu, micrograms per deciliter, turns out to be, the average for these children turns out to be 6. Okay, that's bad because I think the action level is 5, but I'll call it 6. And the standard deviation is equal to 2. Okay, and let's say for our purposes, this is normally distributed. Now, notice I'm using mu and sigma. I'm not using X bar or standard deviation, right? I'm not using them because I'm describing a sample that involves the entire population. This is the rare event where we actually know what mu is. So I'm going to sketch this out because it's always going to be easier to figure this out if you draw a little bit of a sketch. Okay, so this is what this distribution is going to look like. Mu is equal to 6, and the standard deviation is equal to 2. So 1 standard deviation above the mean is going to be 5. It's going to be 4. 2 standard deviations below the mean, I said above, I meant below, is going to be 2. And similarly, 1 standard deviation above is going to be 8. Sigma is 2. And 2 standard deviations above is going to be 10. Okay, so if I were to ask you, what percentage of these children had a blood lead level greater than let me start with rather than that, would have a blood lead level between 4 and 8. What percentage would that be? Right. Yeah, 68%, right? Pretty reasonable, right? What percentage would have a blood lead level between 2 and 10? 95, right? Seems simple, right? Good. Keep that in mind. It's simple. It's going to get a little more complicated as I move forward and so on. Okay, so what percentage would have a blood lead level that's less than 4? Okay, so here's 4, right? So, yeah. So if I figure this out, yeah, very good. 16. How do we get that? We got that because we know between 4 and 8 is 68%, right? So that would mean between 4 and 6 is 32 because one of the properties we know about this normal distribution is it's symmetrical. So 34, excuse me, 34 and 34% on either side of the mean. And that would leave, since this is 50% is to the left of the mean, that would leave about 16% here that's less than 4. How about greater than 8? Let's say greater than 8. What percentage is greater than 8? Well, that would be this area here. And using the same reasoning, that'd be 16% again, right? Well, how about less than 2? What percentage of the population would have a blood lead level of less than 2? That'd be this area down here. What do we know about the two standard deviations between above and below the mean? Right, that would represent 95%. That leaves 5%, 2.5% in the upper tail, and 2.5% in the lower tails. So this is 2.5%. So now, how about what percentage of the population has a blood lead level between that's greater than 4? Whoops. Let me think about this. Greater than 4 and less than 10. Okay, going to get a little bit more complicated now, right? Well, greater than 4 and less than 10. Well, I know that this area less than 4 is 16%. And I know this area greater than 10 is 2.5%. So I've accounted for 18.5%. And the rest is between 4 and 10, right? So it would be basically 81.5%. Okay, so did I lose you guys online? Are you comfortable with this? Okay, good. I got at least one answer on that. Good. All right, so moving on from that, now we're gonna take a look at this from another perspective. It's very nice to look at this information and use the empirical formula, except we're never, most of the time in real life, we're not going to get numbers that are quite as smooth and easy to work with as this, right? So now let's take a look at what happens if I complicate this just a little bit. Now this time I'm going to be looking at, let's say, the average number of emergency room visits per day in New York City, right? And I'm gonna say it's, like let's say that we measured it every day for years and years, and mu, the average number comes out to be, uh, uh, let's say, 420, and the standard deviation, the spread, comes out to be, let's say, 30. Okay, so now if I draw that normal distribution, assuming it's normal distribution, the mean mu is going to be in the center. It's going to be 420. Okay, and the standard deviation is going to be 30. Okay, so now let's say I wanted to know, first of all, something easy. What percentage of what's the probability that I would pick out any given day, and check the number for that given day, and on that day it would be less than 420? Opinion online? 50%, right? The mean is 420, so 50% of the time you're going to get a value, an individual value less than 420. Okay, so now using what we know, what's the probability that on a particular day that we would get less than 390 emergency room visits. How many standard deviations below 420 is 390? One, correct? So I know I'm dealing with the same situation I had with the empirical formula, and this area is going to be about roughly 16%. So I can predict that like 16% of the time we'll have fewer than 390 admittances or emergency room visits on a particular day. So, okay, let's take this to the next step now. What's the probability that I would have, let's see, less than 380 emergency room visits on a particular day? Well, 380 is now less than more than one standard deviation away from the mean. So it's going to be a lot harder for me to figure this out. I can't use the empirical formula. So I have to know how many standard deviations below the mean is the value 380. And that's easy enough to figure out. Z, which I'm going to use Z to be the term for number of standard deviations, is equal to X minus mu over the standard deviation. If I looked at it for 380, it would have been 380 minus 420, which is 30 over 30 is equal to 1, right? So this time, though, it's going to be equal to 390 minus 420. Did I say 390? I said 380? Yep. Minus 420 over 30. So that's equal to 40 over 30 is equal to 1.33 standard deviations below the mean. So now, in order to figure out what this area is here, I can't use the empirical formula because it only works for whole numbers. It's an approximation, number one, and then it's only an approximation that you can use with the whole numbers for the standard deviations from the mean. Okay, so instead, I need to use some other mechanism. One of those mechanisms that I can use is a table, right? I'm going to go, so you have them on Blackboard in this session for this session. I probably post them for every session going forward from here on out. Okay, so let me see if I can't find it here. Actually, maybe I don't have it. Yeah, I certainly could. I also have it here. I like to use Agresti. Central limit, consonants, influence, types of studies. I didn't download it for some reason. Okay, that's okay. Agresti, this is another textbook, Z table. Okay, Z tables. This is, if it's not on this session, it's on other sessions. It's on the last, it's in the session, we're on session 4, right? It was on the session 3 folder for sure. Okay, so this is the Agresti Z table, the one that we were working with the other day. Notice that the way that this Z table works, it shows the probability, the area of the normal distribution that is below that Z-score. So anything below the mean, because X is a smaller number than Z, when we say X minus Z, it's going to be a negative number. Because anything below the mean is a negative number, this Z-score is going to be negative, and all of these values on this first table are negative numbers because they're to the left of the mean until we get to 0, which is the same thing as the mean. Okay, and then on the other side, if we had a z-score of plus 1.33, we'd be on the right side of the mean, and those are all going to be positive numbers. And that z-score from this table will indicate the area from the z-score down to the left. This particular table always uses from that z-score down to the left. Okay, so I'm going to go in here and I'm going to look up the z-value for the area of this distribution for the z-value 1.33. So 1.30123, you recall that this represents the third digit, so 3 would be in this column. 1.33, and that is 0.0934. Okay, so I'm going to go back to my table here. So this probability would be equal to 0.0934 or 9.34%. That's the area here. That's the probability that I would choose an individual, randomly choose a date over the past 10 years or something like that, and find that the number of emergency room visits was less than 380. Would be 9% of the time that would occur. Okay, you want to go back to the table? Yes. Let's go back to the table. I think I got a question there about that table. Did I pick the wrong one? Oh no. 1.33012. Uh-oh, you're right. Yeah, you're right. 0.98 times 18. Is that what you were at, Angelia? Is that what you were talking about as well? Okay, yep, I got it wrong. I'm old. Forgive me. 1.918, I think it is, something like that. Okay, but you got the right idea. Okay, so that's the way this table is going to be used. It's going to give us areas that we can predict here. So now, if I wanted to know what would be the probability of randomly selecting a date when there were more than let's see, more than 440 days, 440 visits, right? Well, what's the probability of that happening? Well, again, we use our calculation of z. It's going to be equal to 440 minus 420 over 30, and that's going to be 20 over 30, or 0.67. Okay, I'll round that up a little bit. I'm only using 2 digits because I know that's all the table's going to give me. Okay, so I'm going to go back to the table now and look up what that area represents. Now, it's going to be positive because it's to the right of the mean. So it's showing up 0.6. 1, 2, 3, 4, 5, 6, 7 represents 0.7486. Okay, that area then to the left of that is 0.7486. That's that whole area to the left of 440. Right? So if I wanted to know what's the likelihood of choosing someone that choosing a day that's over 440 admittances, well, it's going to be equal to 1 minus 0.7486. So that's going to come out to 0.2514, I guess. I think I got that right. It's about 25% chance that you would pick a day where they have more than 440 people admitted that visit the emergency room. Okay, if this was indeed a normally distributed population,
Professor?
I have no reason to think it really is, but I just needed to come up with some numbers. Okay, so we could go through a lot of permutations of this, but that's how we would do this. If you wanted to, you could actually look up these values using Excel.
Professor?
Yes.
Hi, it's Angela. Could you just go back to the part where you subtracted 1 from 0.7486?
Yeah. Okay. I'm gonna
Thank you.
I'm gonna mute you. Oh, actually, I won't mute you yet. Okay. So what I did there was the table tells me that, first of all, what I did was I determined that 440 is 0.67 standard deviations above the mean. In other words, z is equal to 0.67. Are you okay with that calculation?
Yes.
Is that a yes, Angelia?
Yes.
Okay, you're okay with that. Okay, so now if I go to the table and I look up that area, and that's going to be the area to the left. If I look up what that area is on the z using the normal distribution table, if I look that up, that z-score is 0.0601234567. That tells us that the area to the left of that z-score is about 75% of the distribution, right? So
All right.
since since I was looking for the percentage of people that were higher than the percentage of sample of the population that was higher than 440, I don't want the area below. I want the area above, right?
Okay.
So I can look at this two ways. I can look at the whole area here as 100%, or I could look at this whole area here as 1. So if I look at it as percentage, I would take the 75%, 74.86, 71%, and subtract it from our 100 to get our 25%. If I look at it
Okay.
as the value 1, all the possible outcomes, then I would take the 0.7487, it says 0.75 probability, and subtract it from the number 1 instead of from a percentage. Okay, and that leaves me with 25.25 or a 25% chance, a 0.25%, 0.25 probability. Okay, so all I'm doing there is I'm using 1 in place of 100 to describe this area.
Right.
Is that okay?
Yes, makes sense. Thank you.
Okay, no problem. I'm gonna mute you. Just yell in the chat box if you want to tune in again. So at any rate, so I'm gonna move forward from there. So that's basically the way we would use this. I'm gonna do one more thing just to point something out to you. Okay, and that is, let me get another clean sheet here. Okay, so this is going to be important to us as we move forward. Remember that empirical formula? Well, all that time I spent talking about the empirical formula while I was lying to you. I'm going to take a distribution where the mean is 100 and the standard deviation is equal to 10, just make it easy numbers to work with. And in the empirical formula, I told you that 95% of the population or samples or of the population, values of the population, is between 2 standard deviations below and 2 standard deviations above the mean. In other words, between 80 and 120 in this case, since sigma is 10, right? Well, that would leave 2.5% here and 2.5% here. Or as we were just talking about before, I could define that as 0.025. Same thing as 2.5%. Below and above. Well, let's actually do this now with the table instead of doing it with the empirical formula. So if I did it with the table and I asked what percentage of the people in this population have a whatever this is blood pressure below 80, what percentage would that be? Would it be 2.5%? Let's check that. Okay, so I'm going to say z is equal to 80 minus 100, x minus mu. X is the value we're looking at, which is 80, over 10, that's equal to 2. So let's go look up a z-score of 2, what area z-score of 2 actually represents. So let's go here. So it's a negative 2 as it turns out, right? So it's going to be on this chart. And it's going to give you the area, which we think is 2.5% based on the empirical rule. Let's see what it really is. 0.02, let's see, the 2.00. Oh, well, look at this. It's not 2.5%. 0.0228. Let me pull that back up here. So it's not 2.5%. It's not 0.025. It's 0.024. What was it? 0.028, right? 0.0228 or somewhere around that. It's less than that. So that's a problem. Really, 95% of the population is not that far over. It's a little less because we need to get that to not 2.5. It's going to be a little bit to the right of that. Well, remember, we could do this. We could use this table backwards. We could use this table to tell us what the z-score is for a particular area. So I'm going to use it backwards. I'm going to look for the area 2.5%, 0.025. 0.025, let's see, 21, 29, 27, where is 0.02, excuse me, 0.026, where is it? Let's see. I'm looking at here it is right there. There it is right there. Okay, 0.025. Well, what z-score is that? It's 1.96. So really, the z-score for 95% on either side is not really 2. It's really 1.96, right? Minus 1.96 and plus 1.96. Standard deviations from the mean to represent 95% of the population inside, right? So that's very interesting. Just so you know, there's a couple of other interesting numbers here. Just to let you know, if instead of that I were 1.68 standard deviations, 1.64 standard deviations to the left and to the right of the mean, that would represent 90% of the population, right? And if I were 2.58 standard deviations to the left of the mean and to the right of the mean, that would represent 99% of the population, leaving a 0.5% here and a 0.5% here. How do I know that? Because I can go to the table here and I can find those values in the table. I'm not going to bother to do it, but if you go there and look for what 2.58 represents, it represents basically 99, 0.5%. So 0.5% here, 0.5% at the top end leaves 99% in between. And if you look up 1.64, 1.64 would represent an area of 5% to the left, and that would mean 5% to the left and 5% to the right would leave 90% of the population in between those two numbers. So what does that tell you? That tells you while the while the empirical formula is nice for quick calculations and also to kind of check your work in case you're using the table, you can go back to the empirical formula and see if your answer looks reasonable, right? But the key takeaway here is that the real value for 95% of the population, left and right, is 1.96, not 2.0. Okay, so in the future, when we start talking about 95% of the middle and 95% of the population, I'm going to stop talking about it being 2 standard deviations away from the mean. I'm going to continue to talk about it being 1.96 because it's going to be a little bit more precise. Now, just so you know, as a reminder, you can always use Excel to help you with some of these calculations. For instance, if I didn't want to use a table, I could look up norm S dist parentheses, and then it asks me for what the z-score is. And if I put in a z-score of 1.96, what does it come up with? It comes up with 97.975. What is that? Remember, I just put in a positive, so that means 97.5% of the distribution is to the left. That leaves 2.5% to the right, just what we would expect for 95%. If I put it in negative, parentheses, negative 1.96, well, I would expect to get 2.5% there because that's the area I would expect to be to the left of this. And indeed, I do get 2.5%, or certainly very close to 2.5%. Okay, it's a little bit tricky, but you can use Excel to do this for you as well. Now, during the last class and on Blackboard, there's a PDF file that has 5 or 6 functions like this: norm S dist, norm dist, norm inverse, binom dist. So there are a series of 5 or 6 functions in Excel that you can use to avoid tables and doing some calculations and so on. In real life, you probably will be using, when you do real data collection and real analysis, you probably use something like SPSS or SAS or some other program that's specifically a statistical program. But for your calculations, and if you want to check your work, there's ways you can do this in Excel too. So I don't want to beat this to death right now. So let's just keep that in mind. Okay, so now I think, let's see, what should I do now? Okay, so we got kind of that out of the way. So that's where we go. So that's where we are now. We kind of brought ourselves back to the point where we left off on Monday. Okay, so now let's take this to the next step. We know that, for instance, we know that if I have a population, okay, and the mean for that population is 90, and the standard deviation of the population, notice I'm using Greek letters, population is equal. By the way, you guys remember what we call these, when we're talking about the population, what we call these values? Starts with a P. It's a parameter, right? parameter, right? As opposed to X bar and standard deviation, those are statistics. Okay, these are parameters. We're working with parameters. So this population, mean is 90, and the standard deviation is equal to 10. 90. And let's see, then this would be roughly 80, and this would be roughly, 100, and this would be 110, and this would be roughly 80, this would be roughly 70, and this is pretty much what this distribution would look like. Okay, so now I'm never going to know what this is, right? I have no idea what that is. I will never know for certain what it is. The only thing that I will know, I probably won't know, I probably won't know this either, but we're going to play around with this a little bit. And since not knowing either one of these things is going to make things complicated, in a lot of the problems for now, for this week, we're going to make believe that we know what the standard deviation is, just because of the population is, just because we want to keep things simple for now, and just make mu our unknown, just make the population average our unknown. So now let's say I take a sample from this population. If I were to randomly sample a person from this population, they could have a value between, say, 65 and 120, right? Maybe 60 and 120, right? But more likely it's going to have something closer to 90. So if I take a bunch of samples from here, right? That sample, when I take the average for that sample and calculate X bar, that sample is going to be an estimation of what mu is, right? So let's say I take that sample, and that sample comes up to be 88. There's no guarantee. I'm going to take a sample. Let's say the sample size was equal to 25. The average of my sample, those 25 people that I took randomly from this population, came out to be 88. Well, that's interesting. I get an 88. That's all I know about this population. I don't know that secretly it's really 90. I say to myself, well, sample size of 25 is pretty interesting. Uh, um, but I don't know it for sure. Let's take a bigger sample. Take a sample of 100. Let's do it again. Randomly check all these things. Let's take X bar. And maybe this time I get a sample, number 101. Okay, well, I'm sorry, not 101. Yeah, 101. Oh, excuse me, not 101. 91, let's say. I want something closer. 91, right? So let's say, I'm still not confident. Let's take a sample size of 100,000, right? So let's say our X bar comes out to be 91 again. Who knows what it might become, right? The problem here is that no matter what size sample I take, I'll never know what mu is. It's always going to be an unknown to me, right? So it would be good if I understood how much it would help me to take a sample size of 1,000 versus 100 versus 25. How much more reliable is a sample of a larger size than taking a smaller sample? Is it really worth doing that? At what point should I quit? How big a sample should I take in order to understand how my sample size really affects my understanding or my likelihood of knowing what the sample mean is? I have to understand how samples work, right? And I'm going to close this out and get a fresh sheet of paper, and we're going to look at what samples look like. Okay. And then we're going to take a quick break because this could get pretty intense pretty quickly, I think. Okay, so let's take a look at that same population I just drew. Okay, we don't know what mu is. Right, this is mu. We happen to know the standard deviation is equal to 10. Whatever reason, we know that. Okay, so if I take a sample, a repeated sample of size 25, right? The range of values that I would expect for here is I would expect 30 below the mean and 30 above the mean would capture like 99.7% of the population. Remember the empirical rule for 3 standard deviations and 3 above. Okay, let's say that if I take a sample size of 25, right? Let's say I don't take that sample once. Let's say I take that sample 100 times. I sample 25 people. I get a number. Number's 89. Sample another 25 people. Get a number. 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 Let's say I do that 100 times. Now I take those numbers and I find the average of all of those sample means, right? Not the average for the population, the average for the sample means. Are they going to be more spread out or less spread? If I draw another distribution for them, the way they're spread out, are they going to be spread out more, less, or the same as my population? How about you guys online? What do you think? More, less, or the same? How spread out will those numbers be? I'm waiting until I get some answers. I got one same. Keep going. Anybody else? Come on, pipe in. Less. I like less better. Okay, less. Okay, we got a couple of lesses there. Okay, and one question mark. They're going to be less spread out. Think about this. The individual values. Let's say this is blood pressure. The individual values for all the different people, you might have somebody that has a blood pressure that's 70, right? I mean, it won't be likely because they're pretty far away from the mean of let's say 100, right? But they're pretty far away. Or you might have somebody with blood pressure of 130, right? But they're pretty far away at the top end. But you could get a value that big. But if you randomly sample people in here, the only way you're going to get a number as low as 70 is if you happen to get 25 people that are all the way down here. That's very unlikely in a random sample, right? In a random sample, you're going to get some below, some above, some below, so that the number that you wind up with is going to be closer to the mean than these individual values. So all of these values are likely to be closer to the mean than the individual. Remember that these are each one of these is a random sample of 25 people from this distribution and the average of that sample, and then another average of 25 people, another average of 25 people. So these numbers are almost guaranteed to be closer to the mean than the individual blood pressures are. So what is that going to look like? Well, we know that the samples approximate the population mean. So what's going to happen is, I don't have much room here to do this, but I'll try and draw it as best I can. What's going to happen is that the mean of all these sample values is going to approximate the population mean. Maybe I should call that 90, which might be 90, but the spread is going to be much smaller. So now instead of a standard deviation of 10, maybe the standard deviation is something like 2. So 95% of these values, instead of being between, say, 20 below, 70, and 100 and 110, now maybe these sample means are going to be more likely to be between 86 and 94. So if I would take a bigger sample, then these numbers might be closer to the mean, and it might even be a narrower distribution. So in any case, when you take a sample, you take an approximation of the mean. In other words, you're after mu approximate your x bar, approximating what mu is. But then the bigger the sample you take, the more likely that you're going to be closer to the mean. Doesn't mean you're going to be at the mean. Sometimes you're going to be below it, sometimes above it, but your standard deviation for the values that you might have got for your means, if you did it over and over and over again, the same size sample, the variability there would be certainly a lot smaller than the individual values for blood pressure of the people in the population. Does that make sense to you guys? Does that explanation help a little? Exactly. Brian just said we're doing a mean of means. Exactly right. That's exactly what we're doing. Okay. So let's take a break. And then we'll come back and we'll take this to the next step, which is really going to be interesting stuff. Because let's take a 10-minute break, and we'll be back at about whatever it is, 6:20, 6:35, 6:36. Okay, okay, guys, and we're back in business. Okay, so now we're going to do an exercise that I hope will demonstrate the principle that I just was talking about the way that sample means relate, based on their sample size, relate to the population. And that concept, that whole thing, that whole idea put together is something called the central limit theorem. I think that's the word. That might have been the name you were looking for, Brian. It's called the central limit theorem. What does that basically tell us? It tells us a couple of things. We're going to go through a PowerPoint in a little while, but just as for starters, what that tells us is that if we take repeated samples of the same size from a population and we find the average for each of those samples, and then we make a new distribution. In other words, a distribution of sample means that we've taken from a population. We take the mean over and over, take a sample, find the means, take a sample, find the mean, take a sample, find the mean, take all of those means, find the averages of them, and draw them as a distribution on their own. Well, that new sample mean distribution, that new distribution of sample means, is going to be normally distributed just like the population distribution was. It's going to be normally distributed. Not only that, but if the original population is not perfectly normally distributed, the sample mean population will be normally distributed. So it gives us a little bit of leeway. If we have a situation where you have a population that's not perfectly normally distributed, and we're a little concerned about applying some of the statistics we're going to be using, when we take samples from that population, especially as the sample size gets larger, particularly over 30, over a size of 30 or 40, and so on and so forth, sample size, then the results of those repeated samples, the means for those repeated samples from that population, even if the original population was not perfectly normal, then those sample means are relatively normal. So you improve the normality by taking repeated samples. That's a good thing. The other thing is that we can also predict, based on the variability of the population and the sample size, we can predict how variable those sample means are going to be. In other words, if the mean of the population, the mean of all the samples is 100, how likely it is that if we take a single sample, it would be a lot lower than 100, a lot higher than 100. If we understand the variability of those repeated samples based on their sample size and the population standard deviation, then we can make predictions about how well we know the population mean given a sample from that population. Because we understand how chance affects whether we're going to get something lower or higher than the true population mean. It's going to make more sense to you if I actually demonstrate it to you. And to that end, there's a document on Blackboard called Central Limit Theorem Confidence Intervals. I presume you guys can hear me, okay? Okay, good. I'm going to open up that document. And that document actually contains an exercise that we're going to run through. It's going to take a second to load the picture on mine. I'll wait for it. Waiting, waiting. There we go. I think it's about to come up. There it is. Okay. So this exercise is summarized here. Okay, but I'm going to do it kind of like free form so that you guys can look at this, go back over it again, and so on. But for starters, I'm going to start free form. And what we're going to do is we're going to take. I've also given you some other files here. I've given you a table that you saw in that document, and this table has a series of numbers in it, 100 numbers. There's actually 10 rows by 10 columns, so it's 100 numbers. They are approximately normally distributed as it happens. Okay, so these numbers in these various boxes are normally distributed. This is going to be our population. As it happens, population could be anything. It could be 100 people, could be 1,000 people, could be a million people. In this case, this is a population of 100 people. We're not going to measure the mean for these 100 people, right? We're not going to do that at this stage. We could, because it's only 100, and we can use Excel to do that. In fact, I gave you another file, which is an Excel file, which has this table in it already. There we go, there's the table. Okay, so instead of finding the mean for all of these, mean and standard deviation for all of these 100 people, 100 samples, I'm instead going to take a sample from this population. I'm going to take a random sample of size 4 from this population. Well, how do I take a random sample? If I'm right-handed, I might tend to grab these numbers over here. If I tried to just do a phone book thing, just put my finger on it. If I'm left-handed, I might be over there. You ever seen these things on the internet where they say, think of an animal bigger than this, and you think of an elephant instantly, or something like that. They predict what you're going to think of because most people think the same way when you give them certain cues. So you might have a certain prejudice to notice certain numbers better than other numbers. Maybe your age is in here. Maybe your house number is in here. So you can't rely on yourself to randomly pick these numbers. There's many techniques, devices, techniques for randomizing samples. You could do electronically. Excel has a function for taking a random sample. SPSS and R have functions for taking random samples from a population if they have the data from the population. We're going to use a really simple version of that, and that is there's another table here, random number table, and this is literally a book which contains random numbers. And this only has a few pages of this book. These numbers were generated either by a computer or some other technique, and these numbers are numbers from 0 to 9 generated randomly. So what we could do is start anywhere in here. Like for instance, I'll start right here, right? If I start right there, these numbers are random. So the number 59 is random, and the next number is 19, and the next number is 91, and the next number is 54, and the next number is 69. I am going to use these random numbers. I'll start from anywhere in this book. Don't start in the same place I did, right? You start anywhere you want. And I'm going to say that 59 refers to the row and column number on that table, right? So the first number I'm going to work with is, let me get this out of the way. Let me get this out of the way. The first number I'm going to work with is row 5, column 9. Row 5, column 9 is the number 47. I'm going to put that over here. Then I'm going to go back to my table. The next number is 19, which is row 1, column 9, which is 37. And the next number is going to be 91, row 9, column 1, row 9, column 1, which is 46. And the next number is going to be 46 is going to be 98, right? It's going to be 98, row 9, column 8, which is 43, right? I'm going to take those four numbers and I'm going to find their average. And the average happens to be 43. I'm going to make that bold so I recognize it, right? The average I got was 43. I'm going to ask you guys to do the same thing a couple of times. So do a sample of 4, find a random number. I randomly go through this, randomly choose 4 numbers from this population, and find the average, and then give me your result. Okay, so I'm going to go on to the next. I'm going to try it again. 38. Okay, you guys at home do it too. And then type in the number that you get. 64. Okay, what was it here? 86. Uh, 18. And finally, 82. All right. These numbers. That comes out to 58. Okay, so I'm expecting to see numbers come up here on your you guys at home. I'm going to take my numbers so far: 43, 58. Okay, good. Finally, 50, 53, 54. Do it a couple of times. 46. Good work. You know, I can't see you, so if you want to cheat and just pick them out randomly by eye, you could do that if you wanted to. But don't tell me you've done that. I just want to get a few more numbers so I can get a decent idea what's going on here. Oh, 55.5. I'm going to call that 55. I know it's a little tedious going back from the table, but this is the way years ago. This is the way we actually used to do stuff like this. Pick out individuals from a population that we wanted to uh, uh, determine what the mean was. Just maybe one or two more numbers. 58 from Brian. Okay, good. Any more online there? I'll give it another 60 seconds or so, and then I'll just work with what I got. Let me do one more myself. 39. Okay, 38.5. I'm going to call that 38 at 39. I'll call it 38. I was rounding down another one that was might as well. Okay, I'm going to take what I got. All right, so now these numbers represent my population. Let me expand this so we can see it on the full screen. I got to move my little chat box over here so I can see it too. So these happen to be a couple of the ones, the calculations that I did. I took four numbers from this population, averaged them, and I moved it over here. Four numbers, averaged them, moved it over there. That's my repeated samples. So this is my new distribution. This is my sample mean distribution. This is the mean. This is the distribution of sample mean, means of samples of the same size taken from a population. And this is my population. So now I'm going to compare these two values. First, I'm going to figure out what mu is equal to, what the population mean is equal to. Okay, what's that going to be equal to? Well, actually, I'm going to take my sample. I got mu and sigma, right? Okay, let me make this a little wider here. And I have x bar. Let me do this first. The mean for the population is equal to average of all of these numbers. This is population mean. And the population mean is 50.1. And the population standard deviation is equal to standard deviation, parentheses, and I'm going to take the standard deviation for all of these numbers, the entire population, and the standard deviation came out to be 9. Well, let's do the same thing now, x bar and standard deviation for our sample distribution. So what's our expectation here for x bar? Our expectation is that x bar is going to approximate the sample mean, is equal to average of these numbers, and we get, what do we get? 50.6, pretty damn close, right? It was a pretty good approximation. Our sample means is a pretty good approximation of the population mean. Well, let's take a look at the variability. The variability, or the standard deviation for the population, was 9.07. Let's calculate it for our sample. Parentheses, and I'm going to take these numbers, hit enter, and what is it? It's less than it was for the population. These numbers are closer together than the population numbers are. And that makes sense because you're going to average them. You're going to get rid of all the, in other words, here we got a 37 here. But that 37 got averaged out by the other values up to a 43. And we got a 64 here. But that got averaged down to a 58 by all the other values that are there. So you tend to buffer the extreme values. So anytime we take a sample based on the sample size, we're going to get numbers that are less variable than in the population when we look at the distribution of them. I'm going to tell you a dirty little secret. And that dirty little secret is that the standard deviation for the sample is equal to the standard deviation of the population divided by the square root of the sample size. Okay, so what does that mean? That means for a sample size of 4, we expected that the standard deviation for the sample distribution would be equal to the population standard deviation, 9, divided by the square root of 4, which is 2. 9 divided by 4, we would have expected to be around 4 or 5. It turned out to be 7. So we saw a little bit of reduction. But remember this, that this is a relatively small number of sample means. We could have done this, if we had done this 1,000 times, we would have seen almost exactly this outcome, where the standard deviation would have been 4.5 instead of 9, literally half sigma, because sample size of 5. Well, what does this tell us? What if the sample size were 25? Square root of 25 is 5, then standard deviation for our sample means is going to be, instead of being 9, it's going to be 9 divided by 5. It gets smaller. That the variability in these numbers as the sample size goes up gets smaller and smaller and smaller. For 100, then it would be 1, the standard deviation. They'd be much closer together, right? So that's something that's really going to come in handy for us. This standard deviation of the sample means is going to help us understand how likely it is that when we get our x bar, we calculate our x bar based on the sample size we're using, how likely it is that we're close to the actual sample mean. Obviously, as the sample size goes up, the variability of the possible means that we could have gotten goes down, so it's more likely that we're close to the mean when the sample size is bigger. Now, it's kind of cumbersome to call this standard deviation and this standard deviation. When we're talking about the population standard deviation, we often call it sigma, or population standard deviation. When we're talking about the standard deviation of repeated samples of the same size, instead of calling it standard deviation, we're going to give it a special name. We're going to call it standard error. Okay? It's a standard deviation. We're just going to give it a special name so we don't confuse it with sigma. Okay? So, have I confused you guys enough so far? Okay? Well, in practice, this is going to be easier than it is the first time you see it. This is one of those things in life that when you look at it the first time, it seems confusing. It seems counterintuitive. But over time, when you go back and look at this stuff, and you've looked at it a few times, a light's going to go. I guarantee it always. This happens with all students. I have enough experience with this to know. Eventually, a light's going to go off, and it's going to make sense to you. And the worst part about this course is you're going to learn this stuff for the first couple of weeks. We only have an 8-week course here, so you're going to learn stuff first couple of weeks. We take an exam, then we're going to move on to other stuff. The exams are not cumulative, but we're going to move on to other stuff. And then you take another exam, and then at the end you're going to take some little project, or you're going to take another exam. By the end of the semester, when you look back at what we've been doing here, you're going to say to yourself, boy, that was really simple. I don't understand why it seems so confusing when I first look at it. I guarantee you that's the way you're going to feel when we're all done. Right? So at any rate, so that's how this works. So now I'm going to go because I don't know why, but because I think I'm supposed to. I'm going to force you to watch a PowerPoint. Right? We're going to go through a PowerPoint. I know you've probably seen enough PowerPoints in your life at this stage, but I guess one more won't kill you. Okay, so let's go through this PowerPoint. And I'm going to actually post some videos of this PowerPoint being presented by another professor, by Professor Waldron. So you can actually see it two ways. You can see it the way I'm presenting it. You can see the way he presents it as well. You don't have to watch it both ways, but who knows? Might make things easier. Okay, so here we go. No, I don't worry about the fonts. Okay. Okie doke. All right, here we go. All right, so I'm going to go full screen on. Maybe I don't want to go full screen. I don't want to go full screen because then I won't be able to see if you have any comments there. So I'm going to do this way rather than go full screen. Okay, so this is what we're looking at. Variability of samples. Already, what we're doing here, again, reiterated, is we're looking at the idea of what populations look like, how they're distributed, versus how samples are distributed when you take repeated samples. So we're going to be looking at sample distributions. That's when you take a sample from a population, find the average for that sample, and then repeat it over and over and over again, and put together a new distribution, which is only sample means. Okay, and then we're going to apply the central limit theorem. What was that again? That central limit theorem tells us there's a relationship between the sample size and the variability of the distribution of samples. It also tells us that when we take a sample from a population, this sample distribution, even if the original population wasn't perfectly normal, the sample distribution, if the sample size is big enough, is going to be normal instead. Then we're going to talk about study types a little bit. That's really going to come in at the end. We're not going to beat that to death. I think we did a little of that earlier on. That was in one of the videos earlier on. Okay, so let's talk about population versus sample. Okay, so when we're talking about a population, the symbols that we use Greek symbols. We mu for the average and sigma for the standard deviation or variability, in other words. Okay, so now if I looked at New York's, this is actually this actually looks like Maine, yeah, Massachusetts, right? There's Cape Cod, right? So this is everybody in Massachusetts. So their average blood pressure for everyone in Massachusetts turns out to be 78. Chances are we'll never know that in our lifetime if that's really true, because we'd have to measure everybody's blood pressure in Massachusetts. Not very practical. But the mean that we're talking about here, that's a mu. Mu is 78. We probably will never know what mu really is, but in the background, secretly, we know it's 78, right? So now, if we want to understand what mu might be, we might do that by taking a sample of people in Massachusetts. So for instance, we may take a sample, randomly sample 100 people from Massachusetts and get a mean of 75. We might sample 10 people from Massachusetts, get a mean of 67. We might sample 25 people from Massachusetts, get a mean of 71. We might repeat this again, 100, might get 76 this time. So these selections, random selections of people in from a population, the reason why we do that is because it's the only practical way for us to determine what the average blood pressure is for the entire population. Okay, because we can't afford to sample everybody in that population. Okay, so the idea here is that we're making an inference here. We're saying that the sample mean approximates the population mean, or mu. So, and in fact, it does. In one case, it's 3 away. In one case, it's further away. In one case, it's a little closer than that last one. It's not exactly the same as the population mean, but there's no way for us to know whether it is or not, because in most cases we would know what this number is anyway. So, but that's what we want. We want to be able to predict what the population mean is based on a sample from that population. As the sample gets bigger, it's likely that we're going to have a more accurate view of what the population mean is. But we need to, but we could actually wind up with a large sample that's not as good at predicting as a small sample just because of chance, right? So we need to understand how likely it is, or how I can determine the how well my sample is predicting the population mean. So we're going to look at a good way to do that. Okay, so a few words. Study units, the sampling units, those are the individual elements of interest, like the blood pressure and the individual people that you're sampling. The target population is the population that we want to describe, that we're really interested in. That's the population of Massachusetts in this case. The study population is the population that we can actually sample from. To give you an example of that, let's say we wanted to survey, we want to measure the blood pressure of everyone. Well, we're going to do this by phone. We're going to call people up, ask them their blood pressures, right? So our target population is everybody in Massachusetts, but our study population is only going to be people that have phones, right? We can't get to everybody. Not everybody has a phone in Massachusetts. So if they don't have a phone, they're not going to be part of our actual study population. It's a little bit of a difference, right? You try and make your study population as close to your target population as possible. Sometimes that's not practical, though. Whoops. Okay. And sampling frame lists of all units, all the units in the study population used for sampling. We're going to be talking about that as we move forward. Again, Greek letters for population population information parameters. I didn't mean to call it statistics, like mu and sigma. English alphabet for sample statistics, like X bar for the mean and S for the standard deviation, the corollary to mu and sigma for the population. Okay, sampling strategies. What we did before, what we just did in our exercise, was called a simple random sample. We had a population, and we randomly sampled people from that population without regard to where they were, who they were, what groups they might belong to, and so on and so forth. Simple random sample. Very often, that's the way that you're going to do that. Okay, now there might be reasons why we might do a more systematic sampling. Okay, so for instance, if we were going to base our sample on say Social Security numbers, and we're going to take and since Social Security numbers basically are pretty random, right? There's no particular pattern for them. You might say, well, I'm going to start with somebody who's Social Security, and you have a list of people and their Social Security numbers from that population. You might say, well, I'm going to start with Social Security number 1500. The last 4 digits are 000, and I'm going to pick every 10th person. So the next one might be 0010, sample M, 0020, sample that person, and so on and so forth. So you could have a systematic strategy, which gives you which could also be a relatively random sample as well, especially if you're choosing some value, some way, some strategy for doing it that is essentially random anyway. The next one is stratified sampling. For instance, let's say I wanted to do a random sample by phone of all the people in New York City. Well, if I randomly pick out numbers and call people in New York City, I may find that, for instance, I call 1,000 people. I may find that 200 of those people live in Manhattan, 300 of them live in Queens, 100 of them live in Staten Island, and a couple of hundred of I lost track of what the numbers were. A couple of hundred live in the Bronx, and so on and so forth, and Brooklyn. And I may find that, gee, I got just from my random sample, I got too many people from Manhattan and not enough people from Staten Island. So you say, oh no, that could be a problem. I'm already biasing the study even after I've just started with my random sample. You might say to yourself, let's stratify this. Let's instead of doing it that way, let's look at the population of Staten Island, and let's say the population of Staten Island is 1/10 of the population of Manhattan, right? You may say to yourself, okay, well in that case, I'm going to randomly sample 1,000 people from Manhattan, but only 100 people from Staten Island. So you eliminate the bias that you might have had if your samples were not weighted by borough. If that's what you're worried about, if you think there could be a difference by borough, like for instance, if you're sampling for attitudes about about tax increases, right? Attitudes about tax increases, or maybe a political poll. You might say, well, Staten Island is going to vote differently than Manhattan and then Queens and so on and so forth. So you might want to, that's the kind of thing you might want to stratify, because if you overweight, you get too many people from Manhattan, it's going to throw your poll off. If you get too many people from Staten Island, it's going to throw your poll off if you're looking for the overall uh, 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 voting result for the entire city. So that's why you might stratify that. How's that? Are we okay with that so far? Make sense? You can, of course, uh, 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 take a closer look at this later on. Natural groupings are it's cluster sampling. Natural groupings like country one, country two. It's that just basically what I just did with the idea of the boroughs and so on. Okay, so now there are also sampling strategies that you use that are not random samples. For instance, let's say that we want to study mesothelioma, right? So, and we want to we want to investigate if a certain exposure, like to asbestos, was likely to have made someone more likely to wind up with mesothelioma. We know that's true, of course, at this stage, but 30 years ago, 40 years ago, we were just gathering the evidence to really prove that, right? So let's say we want to do a study like that. Well, mesothelioma is a relatively rare form of cancer. So the last thing you're going to want to do is randomly sample people in a general population, because very few of them are going to have mesothelioma. Instead, what you do is you go to a cancer clinic that treats mesothelioma patients, and you use those mesothelioma patients as part of your study. And maybe you compare them to another group that's similar in every way, in as many ways as you can, that don't have mesothelioma, to see if there's differences in exposures or other health factors or behavioral things or something like that. Sometimes you're in a situation where you're forced to do that. For instance, volunteers. Very frequently, you'll be doing surveys, and you'll be looking for volunteers for your survey to take your survey. So that's not really a random sample. Some people may be more likely to volunteer than other people. Okay, so and yeah, we're really not sure about how much bias we're introducing when we do that. Okay, but certainly not random. Okay, then this is geographical random. This is the various kinds of sampling techniques, kind of illustrated using GIS or graphics. Okay, population versus sample. And this is really just what we just did. Um, uh, uh, let's see. This is the results of almost 17,000 people in a 10-mile race in Washington, D.C. Cherry Blossom Run. We just missed the Cherry Blossom Festival this spring. Yeah, here in New York at Brooklyn Botanical Gardens. Is this a sample or a population? What would you call that?
Population.
That's a population. You guys agree? Yeah, good. We got a couple people on here. Right, population. We're still awake out there in TV land. Right. So at any rate, that's a population. That's everybody that ran the race. This is the result for everybody that ran the race. Their times, I guess it probably would be. So if we took the mean of this, it would be mu. It would be the population mean. Okay, so now that let's take a look at the difference here. We have this is all 16,000 runners. This is a sample, random sample of 100 runners from this population. These notations up here run 16 data set. This was generated actually from the real data. This sample of 100 was generated by random having R, a program R, randomly sample the numbers from this population. And if we look, the middle looks like to be around 90 or 100, and the middle here is around 90 or 100 as well. We also notice that the distribution is similar, right? 40 to 140, 40 to 140. So the mean and the variability seem to be similar for the sample and for the population. Keep in mind now, this is not repeated samples. This is just a single sample from this population. So the mean and the standard deviation of that one sample approximate the mean and the standard deviation for the population. That's why if it didn't work that way, we wouldn't bother to sample things because then they wouldn't help us predict anything about the population. Okay, where things get different is when we repeatedly sample 100 people from this population and do it again and do it again and do it again and do it again and then make up a new distribution, a new histogram from those sample means, not a single sample like this is. Okay, so we take a sample from the population, calculate statistic, repeat. So sample distribution is exactly what we did before. Take a sample from the population, calculate the sample statistic, for instance, the mean, and then do it again. Take a sample from the population, calculate the mean, repeat. And this is a loop. You do this many times. If you do this enough times, you'll get a new distribution from new numbers that is going to be called a sampling distribution. And if we look at the sampling distribution, right? If we look at the sampling distribution, we'll see that the sampling distribution is much narrower than the population distribution. And how narrow it is, how much smaller the standard error for the sampling distribution is from the population standard deviation, or sigma. How much narrower it is depends on the sample size. The bigger the sample size, the closer all the results are together, so it makes for a narrow distribution. Okay, here we go. It's histogram. Let's see. Question: is a histogram of a sample an approximation of population distribution or the sampling distribution? As we said before, it's an approximation of the population distribution, right? Because it's only a single sample. It really represents the same people that are in the population, right? This is that first graph that we looked at, which is just 100 runners randomly selected from here, not a distribution of repeated samples, right? Yep, okay, good. Okay, central limit theorem relates the sampling distribution, the means of repeated samples, to the population distribution. Okay? And what is that? What is that relationship? The standard deviation of the distribution of samples, we're going to call it from now on the standard error, is equal to standard deviation of the population sigma divided by the square root of the sample size. The bigger the sample size is, the smaller is going to be the standard error of the sample distribution. Okay. Okay, and here's kind of an example of that where they've took repeated, in other words, they've taken repeated samples from this population and they showed how it narrows down. Here's larger and larger sample sizes, and the distribution narrows for larger and larger sample sizes. For random sample, let's see. And again, they've repeated that standard error is equal to sampling distribution follows the following distribution, standard error, sigma over the square root of the sample size. That's just, that little box is just a remnant of, remember that it asked me if I wanted to download the font. That's probably because I didn't download the font. Okay, let me get to the next spot. Okay, standard error. Standard error tells us how much variability that we should expect when we take a sample. So if we know the standard error is 10, then versus 5, then we know how when we take a sample, the one that has a standard error of 5 has less variability if we take repeated samples than the one that has a standard error of 10. What does that tell us? That tells us that the distributions, the sample distribution with a standard error of 5 is more likely to give us a good approximation of the mean than a standard error of 10, because the sample result the means of sample results are more variable in the one that has a standard error of 10. Okay, how large a sample should you use? Okay, this is a question that's going to bug us and drive us crazy through the rest of the semester, because you know how time is money? In statistics, sample size is money, right? So whenever we do a study, the sample size that we determine. Remember, if you're doing a survey, you might have to hire somebody, pay a student, intimidate an intern, whatever you might have to do. You might have to do something to convince somebody to put the work in to do this. So some of these studies, someone might have to be interviewed for a half hour, an hour to complete the survey. There might be some medical tests involved and so on. So this is time and money that's involved here. So you want to determine what sample size is going to be adequate to demonstrate your what you think you want to prove or disprove, and so on and so forth. What your study, what the object of your study is, right? But from the point of view of the central limit theorem, for starters, we want to make sure that we have a sample size that's big enough that we can say with some confidence that our sample the distribution of a sample means is is predictably normal, right? And that sample size is, say, about at least 30. When we get up to a sample size of 30, then even if the original population is not normal, the distribution of sample means is going to be approximately normal. So we can make some pretty good predictions. We're not going to really be taking repeated samples over and over again from the same population. We're only going to take one sample going forward. But because we understand the idea of the relationship between sample size and how variable sample results can be, because we understand that, we can then use that knowledge to understand how precise, how accurate, actually, how accurate our sample mean is in predicting our population mean. It makes sense, just a little bit. I think I just repeated that. Okay, we can do the same thing with proportions. Okay, why would I want to do that with proportions? Remember we were talking about the binomial distribution before? I got a question here. Okay, sorry I let that get away for so long. So the data for the sampling distribution so data for sampling is only the means of each, exactly right. It's only the means of each, not the original population information, not individual blood pressures, but only the means of the samples if you take a sample of the same size over and over and over again. Yes, exactly right. Okay, so we can do the same thing with a dichotomous variable. Like, for instance, how are you going to vote? Well, let's say a population in New York City is, let's say the voting population in New York City is 1 million people. 1 million people are going to vote in the next election in New York City, right? So if I went to them and asked them, are you going to vote Democratic or are you going to vote Republican, right? Well, some of them are going to say Democratic, some of them are going to say Republican. But that's not a numerical variable, is it? It's going to be Democratic or Republican. It only has two values, right? So the way we deal with that is that we describe it as a proportion. So if there's a million people in New York, and in the next election, 550,000 of them vote Democratic, that would be the proportion of voters that voted Democratic would be 0.55, right? More than half. 55% or 0.55. 550,000 out of a million would be 0.55. That is a proportion. Okay, so now the only time we're going to know that proportion is when the election occurs and they count the votes, and you will actually know what the true proportion of Democratic voters in New York City are at that point for that election, right? Well, let's say you're a candidate, you want to know what your chances are going into this thing. Like you're a month away from the election, you want to know whether to keep spending money or not spending money on your campaign, and you want to know what's the probability that these voters are going to vote Democratic. Well, you can't go out and ask every one of those million people. So you do a poll. You do a random poll. Might be a stratified or a random poll based on sampling, say, the right number of people from each borough or different age groups or something of that nature. Making sure you hit all the age groups. You might want to get as representative a sample as possible, or it might be just completely random sample. Okay, so if you go ahead and you take your sample, right, the proportion of people in the election that are going to vote Democratic is unknown. You're not going to know it until it's actually counted. However, if you take a sample of size 100, you know that 100 of that 100 people, if 54 out of those 100 people tell you they're going to vote Democratic, the proportion of the people in that sample that are going to vote Democratic is going to be 0.54 or 54%. Yeah, but now, gee, that's interesting. But how is that distributed? How likely is it that I take this sample again and I would get a lower number or a higher number? In other words, maybe I can do the same thing I did with my sample means for a numeric variable like blood pressure. Maybe I can do the same thing for a proportion, and indeed you can. So your proportion P is the percentage that you get on any given out of any given sample. In fact, similar to X bar, we call the P that we get from a sample P cap, right? P with a little cap on top, right? In fact, you can see the little cap over here on the bottom, right? So we can take repeated samples from a population and ask them over and over again, you're going to vote Democratic or Republican, just two answers, and one time we get a proportion of 0.45, another time 54% voting Democratic, 48%, 52%, 56%, 51%, so on and so forth. And they're going to be distributed a certain way. And in fact, you can actually calculate a standard error, a standard deviation for the proportions, for the results of the proportions. As it happens, the formula for that, the standard error for the proportions, give you a variability of proportions, is equal to the square root of P times 1 minus P over N. So if you took a single sample of 100 people that came out to be 0.55, the standard error would be 0.55 times 0.45, 1 minus P, divided over 100, and then you would take the square root of that whole thing. And that would give you your standard error for proportion, just like your standard error for your for numeric means. Okay, so how do we apply all this stuff? Okay, well, if we have a large enough n, we can make predictions about uh, uh, what our true population mean is and how well we have predicted our true population mean. Okay, so if I look at this formula right here, what does this formula right here tell me? Okay, this formula tells me that whatever my population mean is, whatever my sample mean is, minus my population mean over my standard error, that's the amount of difference between what I predict the population mean is and what it actually is. In other words, this is what I got from my sample. This is what I got from that's the actual population mean. And because if I take repeated samples of a certain sample size, well, then the difference between these two, if I wanted to relate it to z-scores or standard errors, I would divide it by the standard error, sigma over the square root of n. So this number, this z that I have here, represents how far apart the mean and the population mean and the mean that I got from my sample are. Okay, and inevitably, what I can do with this z is I know that if that z is that the likelihood that that z is 2 standard deviations below what the real population mean is, and 2 standard deviations above what the real population mean is, the chances of that happening are only 2.5% below and 2.5% above. In other words, we're 95% sure that that if we take a sample mean, we're 95% sure that the real mean is between 2 standard deviations below our sample mean and 2 standard deviations above. I just used the wrong term there. What should I have used instead of standard deviation? Standard error, right? Exactly. It's 2 standard deviations below the sample mean, 2 standard deviations above. So in other words, we can be 95% sure that if I calculate my standard error and add and subtract it from my sample mean, that range of numbers is 95% certain to capture the actual population mean. Okay, that's what we draw from that formula. Don't worry about it if you don't see it in that formula yet. Worry about right now worrying about applying this. Okay, this idea, central limit theorem, forms the basis for calculating confidence intervals, which we're going to learn about shortly, doing something called a t-test where we compare means, doing something called analysis of variance where we calculate the likelihood of different means for different populations, more than two means, more than two populations at the same time, and so on. So that this idea of the way samples behave and the way that they're distributed and how the sample size affects them is something that's really going to carry us through at least half of the rest of the semester, this summer semester. Okay, and just to reiterate, I just close out this PowerPoint. Um, 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 uh, Different kinds of studies, experimental studies. I think we covered a little of this in the beginning. I just want to cover it again for a little bit. Different kinds of studies. Experimental studies are the types of studies where you do randomized control trials, where you actually compare two different randomized groups. For instance, a treatment and a control group, where you're testing a drug, for instance. Experimental studies are the only ones that prove causality. In other words, we give a drug and a placebo to someone, a blood pressure drug and a placebo to one group, and a drug to one group, and we take a matched group over here and we give them a placebo, and no one knows which one they took, and so on and so forth. And it turns out that the people in the that took the drug have lower blood pressure than the people that didn't that took the placebo, and we can conclude, since there were no other changes, we had control of the other issues here, we can conclude that the drug is what caused their blood pressure to go down. That's the advantage of an experimental study, is that you have control, you have a control group, a treatment group, you can actually compare, and that's the only kind of study where you can prove causality, that the exposure caused the result. Okay, other kinds of studies make this a lot harder. Observational studies are studies where you don't actually intervene or do anything. You're just observing what's going on in the population. For instance, if you wanted to know what the prevalence of diabetes was in the population, you would randomly sample people in the population and test them for diabetes. Okay, and there's a whole bunch of these that we're going to be working with going on in the future. N. Haynes, the Health and Nutrition study. I'll bring that up in a second. The New York City Community Health Survey, and there's many others. A retrospective study, you look at subjects based on their health status. For instance, if you want to do a retrospective study of cancer patients, you go to a clinic where there are cancer patients and you interview them and you look at their history of exposures and health issues and so on and so forth. A prospective study, you take a group of people and you follow them forward through time. Okay, in other words, the Framingham study is a famous study where they enlisted doctors, tens of thousands of doctors, to report to them their cardiovascular and pulmonary function health, and also there's whether or not they smoked, for instance. So that was a prospective study. They're very expensive, tedious studies because you still, for instance, for heart disease, they had to follow these doctors for decades to see what the outcomes would be for those. So prospective studies are pretty intense to do, pretty expensive to do. People drop out of the studies, you lose track of them, and so on and so forth. So they're difficult studies to do. All of these kinds of studies, for a variety of reasons, don't prove causality. You can prove an association. Oh, it looks like the doctors that smoked were more likely to get lung cancer, but there's a lot of other factors that might have gone on, or them other factors that might have affected whether or not they dropped out or stayed in the study. So they don't actually prove causality. You need an experimental study to do that. But you can certainly infer that there's an association between, say, an exposure and an outcome. Okay, randomly assign never smokers to smoking and non-smoking groups. Follow for years. Randomly assign smokers to no intervention or cessation program. Follow years who develops cancer. It's a couple other examples of this and so on. I'm not going to beat that to death. But yeah, keep an eye on that. You might get a question or two that see cross-sectional survey sample asks whether or not they have been diagnosed with lung cancer and how much they have smoked. Observational, you're not doing any kind of intervention. Retrospective, 50 cases with lung cancer, 50 who do not have lung cancers, and ask them how many it's the people in each of those two groups if they smoked. And prospective, observe groups of smokers and non-smokers going forward in time to see which group develops lung cancer more frequently. Okay, so that's really basically where we stand with this. So let's take a look at where we might apply this. Okay, let's see what I got here. Oh, before we do that, I just want to open a couple of these databases. We're going to be working with databases that have a lot of information about. That's in New York City. I don't want that one yet. Oops. Health data, New York City. Okay, so what happened to the NHANES? Let me start with NHANES. Okay, National Health and Nutrition Examination Survey. It's run by CDC. We also have a local version of this, NHANES, New York City Health and Nutrition Examination Survey, as well. But this is a random sample of participants that have been asked to reply to surveys, and some of them involve some medical testing and so on and so forth. And the object is to collect information about health and nutrition in the population in the United States. Okay, and you can read. You can go to this website. I gave you a link on Blackboard, I believe. If I didn't, I'll make sure it's up there. And you go to this website and you can learn about how this study works, how the participants are selected, the kind of information that's collected, and so on. We're actually going to be working with some of this data later on in the semester as a source of some of these statistics that we're going to work with, and also it's going to be a source of data for if you choose to do a small project instead of taking a third exam. And let's see if I can't find a little bit of there was a video here that I just wanted to play quickly. Okay, where is it? Here we go. Okay, I'm going to play this briefly. If I can get it to work. I'm going to turn the sound up here so Brian can hear it too.
Welcome to NHANES. NHANES, or the National Health and Nutrition Examination Survey, is one of our nation's most successful and longest-running health surveys. As an eligible participant, you will receive a health exam and the exam results, all free, while helping researchers understand health issues in the United States. You may be wondering how you were chosen. You were randomly selected through a statistical process using U.S. Census information. As a selected participant, you represent up to 65,000 people similar to you. We do not accept volunteers for our survey. Your information is important to the survey, and no one can replace you. Let's talk about your benefits for participating. You will receive a health exam and results at no cost to you. Your specific exams are based on your age, gender, and current medical conditions. The results will probably give you a more detailed picture of your overall health than a routine doctor's visit. You will also receive compensation for your time. Here's how you can participate. If your household has been selected for the survey, you will be contacted in person by an interviewer. The interviewer will determine your eligibility. If you are eligible, the interviewer will ask you questions regarding your health history in your home. Then an appointment will be made for a one-time health exam at our mobile facility. NHANES guarantees your privacy. All information obtained from the home interview and physical exam is kept secure. We never give out any information that identifies you or your family without your consent. NHANES data is used for many important national health purposes. For example, you may be familiar with the pediatric growth charts found in doctors' offices to monitor children's height and weight. NHANES data is also often used to identify national health trends. This includes the tracking of obesity, diabetes, and high blood pressure. If you have questions concerning our survey or would like more information, please contact our toll-free number listed on your introductory letter. The number is 1-800-452-6115. We're available Monday through Friday, 8:30 a.m. to 6 p.m. Eastern Time.
Okay, so for you people that are interested in nutrition in the United States, if you're interested in public health in the United States, you can imagine what kind of valuable resource that this kind of survey and this kind of information is going to provide you with. Okay, so we're going to be working with a little bit of this. I encourage it if you want to go to this website. You can just search for NHANES, and you'll see various explanations of how this works, and you'll actually be able to see the actual raw data that's available here, or raw and adjusted data that's available here. We'll be downloading some of this data as we progress in the semester to use it in some of our exercises and projects if you wind up doing it. Okay, and there's a New York City version of this as well. Okay, where it is let's see, is New York City HANES rather than National HANES. See if I can get it to open up. Okay, and here's an overview of it, and so on and so forth. We get some more information about it. And okay, you can actually, it's modeled on the National Health and Nutrition, the NHANES survey as well. And also, we're going to be working with something called the New York City Community Health Survey. And that is a survey that's done by phone, by computer-assisted phone dialers, that target population includes non-institutional adults aged 18 and older who live in New York City household, have a landline phone, and so on and so forth. That's that between me and you, that excludes probably Unless they've changed that, that's going to exclude like half the people I know under 30, right? They don't have landline phones. Only old geezers like me keep their landline phones. And to be honest with you, I never answer the thing anyway anymore. So starting in 2009, adults living in household with only cell phones also included. They've made an adjustment for that. Okay, so at any rate, they sample people throughout New York City. They interview them on primarily a phone interview and collects a variety of information. I think it's something like 150 questions or something like that. I don't know how they reimburse them. You could probably look through this because otherwise I would think it would be pretty hard to keep somebody on the phone for 150 questions, right? Otherwise, unless they got reimbursed or had some other benefit. Okay, so we're going to be looking at data that comes from this study as well. Matter of fact, we can click on here and you can see, for instance, here's all the data that might be collected in New York City from all these various sources. Here's vital statistics, birth and death data for New York City. We're going to be looking at other information like this. Birth data, public health, mortality data. Public health data says mortality data. You can open that up. Annual summary of vital statistics. And here's an interesting looking report here. The most recent one is 2016. You can look at others. The cover to this is always interesting. Okay, let's take a look at what this cover tells us. That's infant mortality, whereas the normal cover has. Did I open one that's just on infant mortality? I didn't open the one that I was intending to. Yeah, I just opened the one that's in summary of vital statistics. Oh, no. I missed my link to the ones that I wanted to. Vital statistics, birth data, public data sets, mortality data. Maybe I clicked the wrong one. That looks a little bit, no, I wound up with the same one. All right, but at any rate, when we have more time, I'll track down the right version. But you can see it has all sorts of data about cause of death and uh, uh, various other kinds of information about racial, marital, geographic distribution of mortality, mortality, and so on and so forth. But a lot of this information this kind of data is publicly available, and we're going to be taking advantage of that moving forward. And you, as you move forward in your careers in nutrition or public health, are likely to wind up taking advantage of a lot of this data as well. Okay, so I'm going to tell you, well, let's take another 10-minute break now, and we'll come back, and I want to get your feet wet on the idea of confidence intervals, okay, and what they mean, and then we'll call it a night. So let's take another 10-minute break and then come back to what we were doing. And I'll resume recording. Okay, guys, I just wanted to come back for about 10 minutes here because I want to introduce a really interesting idea, 10 or 15 minutes. Close out with introduce a little bit beyond what we need to know for the first exam. Maybe there'll be a question on this that'll be for extra credit or something like that. But I just wanted to go over that we're a little bit ahead of the curve here. A lot of the material that I'm talking about now is really scheduled for Monday on the syllabus. But I want to save Monday for doing a review for the exam. In other words, going through all of this stuff, kind of rehashing all of the stuff that we've done since the beginning of the semester that kind of like will put the material on the exam into perspective. The exam will be online. You don't have to come in on June 20th for the exam. You can do it online. I'll put it up a couple of days before and it'll run until Sunday night. You could do it twice. You'll get feedback on what you got wrong, but not the answers. It's open book. You can ask questions on the discussions forum, so it's open to everybody. The responses are open to everyone. So I'm going to reserve this coming Monday, next session, to a little bit of new material, but to a lot of review and preparation for the exam. So that's pretty much where we stand now. You'll notice that after the exam, we talk about something called confidence intervals. I want to introduce that now because that's really an interesting concept and it'll give you a real insight into where this course is going to go from here. So I am going to move this, close this, get this out of the way, open up a blank sheet of paper, and good, I'm glad you guys are back there. I can see you're back. Okay, and okay, confidence intervals. So we just went through this whole thing where we related, what happened here? I seem to have lost my connection here. Let me unplug this and plug it back in again. See if I get my connection back. Let me do this again. Oh, I think that might have done something. There we go. We're back. Okay, so I kind of related this idea of a population distribution. Ooh, that's really ugly. So my tablet here, get it at another angle here, and our sample distribution, sample mean distribution to each other. And their relationship between them was that the sample means x bar mu was approximated by x bar in our samples, and the standard deviation of the population was related to the standard deviation of the repeated samples of the mean by sigma over the square root of the sample size. And that we call the special thing called the standard error. Okay, so we related these two things. We also noticed that 95% of the possible outcomes for a based on the if this were a normal distribution and the mean were 100, we would expect the mean of the repeated samples to be 100, half the time over 100, half the time under. But we would expect that the distribution of those sample means, those repeated X bars that we take over and over again and display here, that they would be between two standard deviations below the mean and two standard deviations above the mean 95% of the time. Well, in reality, not really two standard deviations, but 1.96 standard deviations above and below the population mean. Okay, so we're going to use that knowledge. We're going to put that knowledge to work for us. We're not going to take 1,000,000 samples from a population. We're only going to take one sample from that population. And when I take that sample, okay, I'm going to assume that I have no idea what mu is equal to. I don't know the population mean. But for the purposes, for our purpose for now, I'm going to say that we know what the population standard deviation is, and that it's equal to 25. Now, let's say I take a sample of size 100, right? Sample of size 100, and the mean for that sample, for that 100 individual people that I take a sample from, the mean for that sample is equal to 240. Okay, well, what do I know here? I know that that's a pretty good sample size, and I know that, that sample size gives me an idea that I'm probably pretty close to what the mean is. But I really don't know. I really don't know if the mean is 220. I don't know if it's 260. I don't know if it's 290 or 350 even, right? Maybe I'm way off. I really don't know. And there's no way that I'm ever going to know how close I am on this sample to the mean because I'm never going to know what the true population mean is, right? So I'm going to settle for something else. I'm going to settle for a level of confidence that the mean is close to this number. So if I'm going to start with that number, I said to myself before that I would expect 95% of the repeated samples to be between 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So instead of worrying about how close this is to the mean, I'm going to set up a range that's 1.96 standard deviations, sample standard deviations below the mean, and 1.9 standard deviations sample the standard deviations above the mean away from the value that I found for X bar. Except we don't call them standard deviations when we're talking about the sample means, we call them standard errors. So I'm going to take a formula. I'm going to say that I'm going to also call this, I'm going to give it a special name. I'm going to call it my 95% confidence interval. And I'm going to say my 95% confidence interval is going to be equal to X bar, the mean that I calculated, right? And I'm going to go 2 standard deviations below the mean, standard error below the mean, and 2 standard deviations above the mean. So I'm going to say plus or minus 2 standard deviations. Well, wait a second, though. It's not really 2, right? It's really 1.96 times, and it's since I'm adding and subtracting standard errors, I want 1.96 standard errors above and below the mean. So I'm going to multiply 1.96 times the standard error, whatever that happens to be, for this particular sample. This is the example distribution, and I'm going to add and subtract that from the mean. Well, what is my standard error equal to? Can you count? Do we have the information we need here to calculate my standard error? What do I need to calculate my standard error? The population standard deviation and the sample size. Do I have those? Yeah, I do, right? I have them. So the standard error is equal to 25 divided by the square root of 100, which is the sample size 100, which is 10. So our standard error is equal to 2.5. So I'm going to take that standard error and plug it in here, along with our sample mean. 240 plus or minus 1.96 times 2.5. Okay, and so I'm going to actually do that calculation. It's going to be let me do it over here. 2.5 times 1.96 is equal to 4.9. Okay, so this is equal to, all of this is equal to 4.9 plus or minus 4.9. So I have 240 plus or minus 4.9. So if I subtract 4.9 from 240, I get 235.1. And if I add it to 240, I get 244.9. So what I'm basically saying here is I'm never going to know what the population mean is, right? But I can predict that if I took a sample of size 100 from this population with a standard deviation of 25, I can predict that the true population mean, there's a 95% chance that the true population mean, whatever that happens to be, is between 235.1 and 244.9. That's why we call that a 95% confidence interval, right? Because we're 95% sure the true value of mu is between these two numbers. Will we ever know exactly what mu is? No, but it may be good enough for us to be able to at least be able to understand the likelihood that it's within a certain range. At least now we have some way to measure, what we know about, from a single sample, what we know about the mean. So you guys can imagine that might be valuable to us at some point, right? That's called a confidence interval. Okay, what do you think we might call this number that we add and subtract? This 1.96 times the standard error turned out to be 4.9. What would be a good name for something like that that we're adding and subtracting from a number that we are working with? Think about it. What do you call plus or minus? Oh, that's about 6 feet plus or minus a foot. What would you call that? Give it an English name. There you go. Margin of error. Exactly right. I'm glad you're coming in. Margin of error, right? That's the margin of error. We call that the margin of error, right? So we can calculate confidence intervals if we know if we have some estimate of the population standard deviation, and there's ways we're gonna again, we probably most of the time we're not going to know that, but we have ways around that, But for instance, if I have another situation where we take a sample of size 64, and we get a mean weight of 120 pounds, and the standard deviation for that population, mean population standard deviation weight is 16 pounds, right? We can say that, let's see, our 95% confidence interval is going to be equal to 120 plus or minus, that's x bar, plus or minus 1.96 times our standard error, right? Plus or minus 120 plus or minus 1.96 times our standard error. So our standard error equal to, again, standard error is equal to sigma over the square root of the sample size, which is equal to 16 divided by square root of 64, which is 8. So that's going to be equal to 2, right? So this will be 2. And I'm going to round it off. I'm going to say 2 times 2 is 4. So our 95% confidence interval is 120 minus 4 is 116, comma, 124, right? That's our we're 95% sure the true mean, mu, for this population between 116 and 194. Well, you want to know something? Let's think about this. Anybody remember what number of standard what z-score or number of standard deviations I suggested represented 99% of the population, only a 0.5% lower or a 0.5% higher? Remember what that number was? Bingo, 2.58, right? That we got that from the table. Well, you want to know what that represents then? That represents a 99% confidence interval. So if we do this, 120 plus or minus 2.58 times the standard error, which is 2, right? Well, then we can calculate a range of numbers. I'm going to call it 5 instead of, I'm not going to work it out exactly. I'll call it 5. So this is 115 to 125. We're 95% confident the true mean is between 115 and 99% confident the true mean is between 115 and 125. And if I'm willing to be only 90% confident, and you remember what that number was? When we did it before, it was 1.64, right? Because we don't have to be as far apart. So that one would be 120 plus or minus 1.64 times 2, right? And that would be the 90% confidence interval. And notice something. If I want to be more, which one is wider? Without looking at the numbers, which one's going to be wider, a 99% confidence interval or a 90% confidence interval? Bingo. Why is a 99% confidence interval wider than a 99% confidence interval? The other way. Because in order to be more confident, in order to be 99% confident, you want a wider interval. So that means that you're more likely to be right, that it's within those two numbers. If you're willing to be 90% confident, less confident, you can make the range narrower. So as your level of confidence from increase from 90 to 95 to 99, your confidence interval gets wider. So that's what makes you more confident, that you have captured the true population mean in between. Okay, so I'm going to stop there. So you guys online, is that interesting to you? Right? This idea of being able to, from a single sample, having a way to predict whether or not you're close to the real mean of a population. Pretty interesting, right? Guys still awake out there? Hello? I know you're there. I can see you. I got a meh. Okay. Okay, good. This will be clearer to you. As I said, we're a little bit ahead of the game here, right? So I just wanted to introduce this so that you know that where we're going with this stuff. So on Monday, I'll be posting another assignment, another assignment. On Monday, we'll have a review. We'll be here. If you want to come in and join us here, we'll be here. Me and Brian, anyway, and about the rest of you guys, we'll be here, hopefully. But then on Wednesday, I'll be posting the exam so that you don't have to come in or be online for the exam. You can start working on it immediately, and that'll last through at least through Sunday before the next class, that you'll be able to work on the exam. Yeah, I hope it is pretty interesting, isn't it? I know we got a few other less enthusiastic comments, but it is pretty interesting. It's going to get even more interesting as we go forward. As we get away from the really basic stuff here, you're going to start to see ways that you're actually going to be able to apply this stuff. Okay, guys, have a good night, and we'll talk again on Monday. Bye.
So don't come here next Wednesday.
Yeah.
You're gonna be